The most obvious way to replicate writes is also the most problematic. Log every SQL statement the leader executes, every insert, update, delete, and send those exact statements to followers. Followers re-execute them in order. Simple. This approach is called statement-based replication, and MySQL used it as its default before version 5.1. The problem is that SQL statements that look deterministic often aren't. Consider the function now. If the leader executes update order set updated underscore at equals now, or ID equals 42, and sends that statement to a follower, the follower calls now, at a slightly different time. The two nodes now have different values in that column. The replication has silently diverged. Rand is worse. A statement like insert into samples select rand, *100 produces a different random number on every machine. The follower inserts a different row than the leader. Auto-incrementing columns create another problem. Two concurrent insert statements on the leader are assigned IDs in a specific order. If followers process them in a different order, which can happen in multi-threaded replication, they assign different IDs. The data is now inconsistent. Any statement that has side effects, triggers, stored procedures, user-defined functions can produce different results on followers depending on the state of those functions. These problems aren't theoretical. MySQL worked around some of them by logging the result of non-deterministic functions rather than the function call itself. But the workarounds are fragile. The replication log needs to capture what happened, not what was asked to happen. That insight, capture the effect, not the intent, is what drives better replication designs. If you've read Chapter 3, you know that both B-tree storage engines and LSM tree storage engines maintain a write-ahead log, a record of every low-level change to the storage engine. B-trees write every modification to the WAL before applying it to the tree pages. LSM trees have a crash recovery log alongside the memtable. Write-ahead log shipping is exactly what it sounds like: send the leader's WAL to the followers. Followers apply the same low-level byte changes that the leader applied, arriving at an identical copy of the data files. This approach is byte exact. There's no ambiguity about now, or rand. The follower doesn't re-execute SQL, it applies the same raw storage level changes. PostgreSQL and Oracle use WAL shipping for their replication. But there's a serious coupling problem. The WAL describes changes at the level of individual disk pages and byte offsets. It's intimately tied to the storage engine's internal format. If the leader runs PostgreSQL version 14 and a follower runs PostgreSQL version 15 with a different internal storage format, the WAL from the leader might not be interpretable by the follower. This makes zero downtime upgrades difficult. You can't simply upgrade one follower at a time, because the follower can't run a newer version of the storage engine than the leader. You need to upgrade the entire cluster simultaneously, which requires downtime. PostgreSQL actually documents this limitation explicitly. Its replication uses a format that's internal to the specific version and can't be safely used across versions. For a database that takes correctness seriously, this is an honest acknowledgement of the trade-off. There's a better approach, one that decouples the replication log from the storage engine internals. The solution to the coupling problem of WAL shipping is to use a different log format, one that describes changes at the level of rows and columns, rather than at the level of storage engine bytes. This is called logical log replication, logical because the log captures logical row-level changes rather than physical storage-level changes. Here's what a logical log looks like. For an insert, the log records, which table, the values of all columns in the inserted row. For a delete, it records, which table, the primary key of the deleted row. For an update, it records, which table, the primary key of the updated row, and the new values of all changed columns. This format is completely independent of the storage engine internals. A logical log can be understood by a different version of the database, by a different database system entirely, or by external consumers that want to react to data changes. MySQL has used row-based logical logging in its binary log since version 5.1. This is why MySQL replication is reliable in practice despite MySQL statement-based replication problems in older versions. The binary log captures what actually changed, not what statement was executed. The independence from storage internals enables zero downtime version upgrades. Upgrade followers to the new version first, then fail over to a follower and upgrade the old leader. It also enables something powerful called change data capture. Change data capture treats the logical replication log as a stream of events that external systems can consume. An analytics system can subscribe to every change in the database and update its data warehouse in near real time. A search index can update Elasticsearch whenever a product's details change. A cache can be invalidated precisely when the underlying data changes. The replication log becomes an integration bus. Trigger-based replication, available through tools like Databus for Oracle and Bucardo for PostgreSQL, takes this further, letting application code react to every data change and write it to a separate table where custom processes can read it. It's flexible but adds overhead. Logical log replication is the approach that scales, it's decoupled, version safe, and opens the door to treating your database changes as a stream of events.